One, two, three.
Welcome to Math for Teachers Module 3 presentation. My name is Robin Surf.
I'm Maria Segura Bolanos.
And I'm Patricia Montgomery.
Let's get started.
Maria, I have a question for you. What is the divisibility rule for the number 2 and 5?
Well, Robin, these are actually two of the easier divisibility rules to remember. So these are my favorite ones because they're easy. Two, if it's divisible by 2, if an integer is divisible by 2, that means that the last digit has to be divisible by 2 or an even number. So 2, 4, 6, 8, 10, 12. So for example, 268 divided by 2 would come out to 134. So yes, that number is divisible by 2. And if you look, this number would be as well because 134 would be as well because it's an even number too. So
Nice.
then we go on to number 5, which means if the last digit of the number is either a 0 or a 5, then it would be divisible by 5. So if we have the integer 8,749, it ends in 9, so that means it is not divisible by 5. So pretty simple.
Perfect.
Nice. Perfect.
Thanks. Patricia, how do you apply the divisibility rule test for the number 11 to 51,051?
So the easiest way to do any number divided by 11 is to just write out all of the digits, and then you're going to alternate between adding and subtracting starting at the tens place. So you'll do plus, minus, and when you work that out, you get 0. And since 0 is not divisible by 11, then you know that the whole number is not divisible by 11 either.
That's pretty simple.
Perfect.
Yeah, that's pretty good. So Robin, can you use the divisibility test of numbers to complete the chart below?
Okay, well, let's go ahead and look at the chart. Basically, they would like to know if any of the numbers in the top row are divisible by the numbers in the left column. So there are certain rules you can ask yourself to find a quick solution. Let's look at the first number in the list, which is number 2. Any number which ends in an even digit will be divisible by 2. So we can ask ourselves this question and going across the row. We're going to go ahead and go through 3 through 11 together. And number 3, are the sum of the digits in the number divisible by 3? No, they are not divisible by 3. Number 4, do the last 2 digits form a number divisible by 4? No, the last 2 digits are not divisible by 4. Let's move on to number 5. Is the last digit a 5 or a 0? Well, yes, the last digit is a 0 or a 5. Number 6, is the number divisible by both 2 and 3? No, the number is not divisible by 2 and 3. Number 8, do the last 3 digits form a number divisible by 8? No, they do not. Let's go ahead and look at number 9. Is the sum of the digits divisible by 9? No, the sum of the digits are not divisible by 9. Number 10, is the last digit a 0?
Nope.
And no, the last digit is not a 0. Let's look at the last number, number 11. When adding the digits with alternating a plus and a minus sign, can that number be divided by 11? And no, due to the sum of the digit rule.
Nope. Okay.
Goodness.
All right.
Not divisible by anything.
All right, and let's go ahead and look at the next question. Maria, solve the problem below using the casting of nines process.
Okay. So the castings of 9 is kind of fun. You basically are going to cast the 9s out of the problem first. So over here we've got 416 plus 7,490 plus 69,844. Supposedly it equals 112,790. So we're going to use the casting out of 9s process to check our answer and find out if that's true or not. So when you do the casting of 9s, basically you're casting your 9s off the island out of the equation. So we're going to get rid of this 9 first, then this 9. We're also going to get rid of the 7 and the 2 down here in our solution because that equals 9. So we're going to get rid of those. And we're going to get rid of the number 9 here. So we're going to go back up to the top, and part of the process is actually breaking down each number. So we're going to take 416 and break that down to 4 plus 1 plus 6, which equals 11. Then we're going to break down the 11 even further, which makes 1 plus 1 equals 2. The same thing with the 7 and the 4 over here. 7 plus 4 plus 0 equals, it actually equals 10. I mean, sorry, 11, not 10. So we're going to, don't know where that came from. We're going to cast him away. So then we're going to break down year 11. 1 plus 1 is 2. And then we're going to go down to year 6, 8, 4, and 4, which is the same. That equals 22. 2 plus 2 is 4. So to find out if we also add our answer, the numbers in our answer together as well. So 1 plus 1 is 2. Now to find out if this solution is right or not, we need to add up all of the numbers that we came up with up here. So we've got 2 plus 2 and 4, which is 8. Of course, we've got 2 here. Now those numbers do not match. 8 and 2 are not the same, so that means this is not the right answer. It's the wrong answer. So our actual answer, if we were to check our work, would be 77,750. And we can break this down using the casting of nines process, which would bring it down to 7 plus 7 plus 7 plus 5 plus 0 comes out to 26. And we've got 2 plus 6 equals 8, which is the same number we have up here. So that means that this is indeed the correct answer. So
Perfect. You explained that really well.
thank you.
Robin, how do you demonstrate the process of nines to check the answer below?
Okay, so basically what they would like to know is if there is an error in any of these calculations and how we can test that. So we will use a process called casting out nines. To do this, replace every number in the calculation by its remainder when divided by 9. So the remainder for the sum of the digits is the same as the remainder of the original number. We're going to start with the first number, which is 416. We're going to calculate the sum of its digits and then divide it by 9. 11 divided by 9 is equal to 1 with a remainder of 2. So 416 divided by 9 is equal to 46 with a remainder of 2. Both of these remainders are 2. The sum of the digits of 7,490 is 20. So what we're going to do is 20 divided by 9 is equal to 2 with a remainder of 2. The sum of the digits of 69,844 is equal to 31. So we will take 31 divided by 9, which is equal to 27, with a remainder of 4. So we're going to take all the remainders and then we're going to add them together. So you'll have 2 plus 2 plus 4, which equals 6. And then you're just going to do the same to the answer. So the sum of 1,012,790 is equal to 20. So we're going to take that 20 and divide it by 9, which is equal to 18 with a remainder of 2. And then 6 and 9 are not equal to each other. So there must be an error in the calculation.
Gotcha. That makes sense. That's pretty cool.
Yeah.
Hey, Patricia, why does the process of 9 work?
So the reason it works is because if we were to break down 2,943 by each number's place value, we could do 2 times 1,000 plus 9 plus 100 plus 4 plus 10 plus 3. And then we want those to be divisible by 9. So the easiest way to do that would be to break them down to 1 plus 999, 1 plus 99, and 1 plus 9. So then we're just going to distribute into all of those parentheses to get 2 plus 2 times 999 plus 9 plus 9 times 99 plus 4 times 9 and then plus 3. So once you kind of put all the things that are the same together, we know that all of the time 9s are going to be divisible by 9. And then we know that we're then left with those same digits that we originally started with in the first place. So what we can always do is just add those numbers up and see if they're divisible by 9, because we know all the other stuff is going to be.
Okay.
Awesome. Thanks, Patricia. You explained that really well.
Thank you.
Patricia, how do you find the greatest common divisor of 9 and 18?
So in order to divide stuff, you're going to want to use factors. So when we start with the factors of the 2, all the factors of 9 are going to be 1, 3, and 9. And then for 18, they're going to be 1, 2, 3, 6, 9, and 18. So since we're looking for what they have in common, we know that they have 1, 3, and 9 in common. And when you want the greatest of something, you want the biggest or the largest. So 9 would be their greatest common
Okay.
divisor.
That's an easy way to do it.
Yeah.
Awesome. All right, and Maria, how do you find the GCD of the set of numbers?
Well, this is actually another way, like Patricia said, you find the prime factorization of the numbers. And here's the way that I did it for this one. You can take 18, and I divided it by 2 at first, so that's going to be 2 times 9. And then your 2 can't divide any further, so we're going to take our 3 down a little bit more to 3, I'm sorry, our 9 to 3 and 3. So that's basically as far as we can go. So that's going to give us 2 times 3 squared, or to the power of 2. We're going to do the same thing over here to our 84, which we're going to start off with, again, I divided it by 2 at first. So 2 times 42 equals 84. Then we're going to break down our 42, which would be 6 and 7. Our 7 is done. That's the lowest it's going to go. We can break our 6 down to 2 and 3. So now we've got 1, 2 2's, be 2 to the second power, times 3 times 7. Those are our last remaining numbers. So if you look at the common overlapping equation, you're going to get 2 times 3 here and 2 times 3 over here. So when you multiply those together, 2 times 3 equals 6. So our greatest common denominator or divisor of those two numbers is going to be 6.
Nice.
Awesome,
I like
thank
the factor
you.
trees. Yeah.
Those are the funnest. I like doing it this way. I think it's
Yeah.
fun.
I used to love those in school.
All right.
Robin, which rod is 9 centimeters in length?
Okay, so given that each rod's number is also length in centimeters, are you able to tell which rod is 9 centimeters long? Well, yes, the answer is actually the yellow rod. When you see it visually, it's pretty simple, but what if I asked you which rod represented 5x equals 20? Well, the answer is 4 minus the light blue. You look at the light blue rod.
Okay.
It's
Right here.
visually to
Gotcha.
see.
Ah,
Yeah, that makes sense. That's pretty cool.
interesting.
Yeah.
That's neat. Robin, again, how do
Hey.
you determine the least common multiple of 2 or more numbers?
Okay, so let's go ahead and look what we're at our graph here. If you go ahead and click, I have highlighted the numbers we're working with in red. You can create or draw a chart diagram just like I'm showing you here. But you're gonna wanna start in the left-hand corner and begin factoring out numbers, which are the divisors. So if one of your numbers is not divisible by that number, simply bring that number down into the chart. So for instance, I'm factoring a 2 out in the left-hand corner. So when I do that, I wanna bring the number 24 below 48, and the numbers 25 and 65 are not divisible by 2. So I simply bring them down. Now 24 is divisible by 2 again, so I placed a 2 next to the 24 to bring 12, 25, and 65 down again. But instead of rewriting the same numbers over and over again, I simply left them blank, and that's for the numbers 25 and 65. So now divide 12 by 2 and you're left with 6, which leaves you with 1, 3, and 1, 2. And then now we can divide the 25 by 5 and 65 by 5, and we're left with 2 5s and a number 13. In order to write these numbers out, it looks like that above. So you can also actually solve those formulas and get the exact answer, but this is not part of this exercise.
Perfect.
Awesome.
Thank you.
You're welcome.
Patricia, how do you determine your answer with the lowest common multiple chart?
So like Robin just showed us how you would do it. I know when I was learning, I had a really hard time trying to keep all my numbers straight. So the way you're going to look at it, if you do fill it completely in, is you're just going to take all those numbers that are on that leftmost column, and then you're going to take all the ones that are on that bottom, and you're just going to count how many of each number you have. So for like this one, you can see that you have 4 2s. So you're going to do 2 to the 4th. And then you have 2 3s. So it's 3 to the 2nd. And then 1 5. So 5 to the 1st. And then 2 11. So 11 squared. And that way it'll equal up your least common multiples.
Okay.
Perfect.
That
I like your
makes-
visual.
That's a lot
Thank you.
more clear.
All right, Maria, I have a question for you. What is the LCM of the following set of numbers?
Well, we've got 16 and 64, and then we've got 12. Well, we'll do the first two first. Now, one of the things we want to remember is we're going to list the first several numbers, multiples of each number. We're also going to look for common multiples for both lists, and then we're going to find the smallest number based off of that. So first, and this is simple, you're just going to take 16 first, then you're going to take 16 plus 16 is 32. 32 plus 16 comes over to 48, and then 48 plus 16 is 64. So bam, that one was super easy. 64 and 64, that's our least common multiple right there. The next one we're going to do is 12 and 18. So we've got 12 plus 12, and then we add 12 to that, so it's 24. Then 24 plus 12 is 36. 36 plus 12 is 48. So now we're going to start off with 18. 18 plus 18 is 36. Then 36 plus 18 is 54. And 54 plus 18 is 72. So our looks right here, it looks like our 36 and 36 were our first common multiple. So that's our least common multiple of those two numbers right there. Super easy. You're just adding that number to itself each time and adding it to the next, or for the first time, and then just adding the same amount to it as you go. These were the easier ones because they have lower numbers, but sometimes you can go all the way up to the hundreds and it takes forever, but that's how you can do it.
Well, and I liked how you list the steps to the right too. That
Yeah,
helps.
it makes it easier.
Thank you.
Yeah.
Just a little reminder.
All right, Maria, I have one more question for you. Would you use the LCM or the GCD to find out how many rotation it takes for the gears to be in the same position and why?
I would use the lowest common multiple factorization to find out how many rotations it takes for the gears to be in the same position. Why? And the reason why would be because that's going to be the first time that those two numbers meet in the middle.
Okay.
So let's say that this large gear has 56 teeth and the small gear has 16 teeth that are rolling over
I
here.
love the animation to it.
I know.
That's
So
neat.
the 56, we're going to start off again. We're going to add 56 to itself, which is 112. Then 56 to 112 is 168. And then 156 plus 168 is 224. Then we've got the same thing. Let me move our faces over here. Then we've got 16. So 16 plus 16 is 32. 32 plus 16 is 48. 48 plus 16 is 64. And then 64 plus 16 is 80. 80 plus 16 is 96. And then finally we get 96 plus 16 equals 112. So this is the first time that our gears are going to meet each other and be at the same rotation. Is going to be at the 112th rotation.
Wow.
It's going to take it a
Very
minute.
cool. Yeah.
All right, Patricia, how do you find the least common multiple of two numbers?
So we are going to be using the same, like the same idea as what you were just telling us with the gears. This is just the way that I find it easiest for myself, is I make like a little chart. And so the numbers on the left are going to be the two numbers that I'm trying to find the least common multiple of. And so up top, that just shows me like how many times I'm multiplying them, what number I'm multiplying them by to get that number. In case we are doing a problem like the rotations and you need to know how many rotations and stuff it's doing. And so I just did them across the board until I found that 60 was where they first make the same number at 5 and 3.
Very
I
cool.
like that way. That's a pretty simple way to figure it out too.
Yeah, I like the chart.
Me too. I'm a chart gal. All right, so Robin, how many additional rotations must the small gear make before A and B are in the same position again?
Okay, so you can see here, I attempted to draw two dots, which are the same points of the two gears. The larger gear has 84 teeth and the smaller gear has 48 teeth. This question would like to know how many more rotations must the smaller gear make than the larger gear before these 2 points come back to the same position again. So let's go ahead and look at the first step. The first step is to find the least common multiple of 84 and 48. So if you make a diagram like we discussed earlier, you can find this number and it comes to 336. To find out how many more revolutions the small gears have to make before A and B, well, they're in the same position again. So you're going to divide the LCM by the number of teeth in the small gear, and that problem comes out to be 336 divided by 48. So the final answer would be 7. The small gear must take 7 more rotations than the larger gear before the dots will come back together again.
Gotcha. Okay.
Nice.
Awesome.
Good job.
Pretty cool. Thanks. All right, and Maria, what is the magic square?
A magic square is basically a square of numbers. You can make it into a 4x4, a 3x3, a 5x5, where the numbers, you have a set of numbers. So we're going to use 1 to 9 on this one, this specific one. Let me I'm trying to find, there we go. We'll put our faces over there. So basically the numbers are, magic square is where the numbers going across, going down, and diagonal are all going to equal the same sum. So with this one, we're going to use the numbers 1 through 9. There are a couple of rules that you want to follow whenever you're filling in a magic square box. You want to put your number 1 as always going to go up in the top middle square. And then to fill in the rest, you're going to go to the right 1 box and up 1 box. If the box is empty up here, that means we're going to go back down to here and put our 2 at the bottom, because that's the next part in the row, basically. It's kind of like a revolving. You're going to make a circle around back to the other side if there's an empty space on the top. So that's where our 2 is going to go. So now we're going to go to the right, which is going to bring us back over here, and then up 1. So that's going to put us right here. That's where our 3 is going to go. Again, we're going to keep going the same process to the right and up 1. Oops, where our box is full right here. So we're going to go back to our 3 and go straight down if the box is full using the right and up method. So our 4 is going to go right there. Then again, we're going to go straight or to the right and up 1. There's our 5. To the right and up 1. There's our 6. To the right, there's nothing there. So we're going to go back over here and then up 1, which is going to bring us back down. Actually, it's bring us to the right and up 1, so 7. And then to the right and up 1 is going to bring us over here to this side for our 8. And then obviously the only number or box available is right here. So for our 9 is going to go down here in the middle. So when you add all of these numbers vertically, horizontally, and diagonally, their magic sum is going to be 15.
Nice.
Perfect.
These are pretty fun.
Cool.
Yeah, it's kind
Yeah.
of like a puzzle.
Yeah, pretty
Yeah.
much.
Cool.
Patricia, what method would you use to complete the magic square?
So for this particular one, if you're just given 9 different integers that you are trying to figure out how to place them in here, and they're done a couple for you, I found that the best way to do it for me was just to do basically just guess and check. So you start out to find out what number you need for them to equal, though. You're going to add up all the integers that they've given you to put in, and you're going to divide it by 3 because it's a 3 by 3 box. If it was a bigger box, then you would divide it by whatever number of boxes there are.
Okay.
So for this one, you would divide by 3, and then whatever answer you get is what it needs to be across or down or diagonal or whatever. And
Okay.
so then I just used, like for this one, since you have 0, 0 plus what numbers would give you that number, and then same with 1, and just guess and plug them in until they all fit.
I
Perfect.
personally like the guess and check method for things.
Yes.
Sometimes it's easier that way.
Just give it a go.
Right. All right.
So Robin, are you able to create a magic square using the integers below?
Well, what is the magic square? It is a square of numbers in rows and columns, which each number is arranged so that the numbers in all the rows, columns, and the 2 diagonals have the same sum. So the good news is that they already supplied us with 2 of the answers. So the first thing we want to do is to find the sum of all given of the integers. So in our case, the answer is -27. Since we know that the sum in each row is the same, then we know that 3 times this sum must be the same as the total sum of the integers. So we can say that 3x equals -27. Therefore, the magic sum must be -9. If we solve for x, now we can use the trial and error to insert the numbers, which each row, column, and diagonal is equal to -9. I started with -7 below the 0. We know that the bottom number must be -2 if the column will equal to -9. And I use -5 and -4 on the very top row because I know -5 minus 4 is equal to -9. So once I do this, I know I only have the numbers -3, -1, and -6 left. It's a matter of arranging them in the right boxes. So you should be able to see that all the rows, columns, and the diagonals are in agreement to -9.
Awesome.
Perfect.
So you can make a magic square with negative numbers as well. Cool. Okay.
Yeah.
Awesome.
Nice.
All right. And that concludes our presentation for modular number 3. See you next time.
Thank you. Bye-bye.
Thank you. Bye.